2016 it came out, which means that, and then Aronson wrote this comic, or contributed substantially, which means he wrote this comic at the exact same time he wrote Ross's letter of recommendation. So hopefully he didn't get those two confused. Anyway, this guy was motivated by some quantum computing stuff, fancy quantum computing, who knows and whatnot. Also, Hoi Nguyen, former student of Vu. These guys, first Aronson, and then together they wrote a paper. But they asked, what if we have this bound, and we have a matrix that's close to the bound? If we're close to the bound, does that mean the matrix has to look special? For concreteness, maybe your permanent is bigger than norm divided by, say, n to the 100. What does that mean? Can we say anything? And then Ross and I proved, yeah, you can say a lot. If your permanent's reasonably big, then virtually every row and every column is dominated by a single entry of large modulus. So it looks very special. It looks very much like a permutation matrix with a little bit of noise, and you just make all the entries just a little bit bigger or smaller. But it really looks staggeringly like a permutation matrix where you have this huge number in each row and column, virtually every row and column. Yeah, fun fact. So that's cool. Let's get into a more concrete version. There are those things again. So if I want to say these results in a little bit more formality, first I want to notice, hey man, you could assume the norm's less than or equal to 1. Otherwise, scale the thing. So we're going to assume the norm's less than or equal to 1. And in this case, Hurwitz's bound says for matrices with norm at most 1, that the permanent's less than or equal to 1. If you're like, I hate this norm, think about orthogonal matrices. That's cool. In which case, orthogonal matrix has permanent at most 1. That's a perfectly reasonable thing to think about. We need this little gadget, which is going to help us keep score. Whatever that is, I wrote down. Ri is the row I of your matrix. But all it is the average of the largest row entries. The first row, the largest entry is this. The second row, its largest entry is that. The third row, pick the largest entry in each row, take the average. So this is going to tell you more or less how big the biggest entries are. And we got this. That this average of the average of the largest entries in each row, that's between 0 and 1. And it equals 1 if and only if the thing's one of these special plus minus 1 permutation sort of matrices. Why does it have to be less than 1? Because it has to be less than the norm. Fun fact. And then here's the results in big boy fancy terms. Ross and I proved that if you got your matrix which is norm at most 1, that's not actually a restriction, then the permanent is bounded by such and such a thing. Which ain't bad. Maybe you want to think about what this would say. For example, if I said, I have a doubly stochastic matrix, for example, and all the entries are at most 0.3 or something, then you'll end up getting a delta which is something like 0.3, and you'll get this squared, and it's saying that your permanent, not only is it less than or equal to 1 or whatever, but it's less than or equal to much less than 1. You'll get an exponential decay, and delta would be a constant here, which is good, and as good as you could do for a doubly stochastic matrix. So that's not bad, except of course for these, what the decay is in the exponent. And if it's, so this works even if the thing's over C. If the thing's over R, we push harder, do some more probabilistic stuff, and we get a result that's better when your thing looks crazy like one of these permutation matrices. When delta is very close to 1, this one ends up being better, whereas otherwise the first one's plenty good. So that's that. Now let me show you how these fit into some context. So let's say we have a bipartite graph, and the max degree is delta. And whatever that is going to be number of perfect matchings. So a stupid result about number of perfect matchings in a bipartite graph is that it's definitely less than max degree to the n. For sure, because you look at each vertex on one side and you say, who are you next to? And he has max degree choices, the next guy has max degree choices, and then you just put all the choices together. It's like a 80s cop show going over the top of a car. So this is somehow an obvious result. I don't know if it's due to anybody. Here's the result of Hurwitz, which I want to put side by side to notice the similarities. The number of perfect matchings in your graph literally is the permanent of your bipartite adjacency matrix. And the norm is doing something analogous to talking about the degrees, but it's not. It's more algebraic than just these degree sums. But it's something in the ballpark of degrees. And these results are, in fact, comparable directly. This one's not obvious because it's not about 0, 1 matrices. It's about matrices. So that makes it more impressive. Not to belittle Hurwitz's result. But you can refine this stupid thing to something better. Bregman's theorem, which says the number of perfect matching is less than or equal to, you can shave off some sort of, whatever that factor is, ends up being about exponential n. You can shave off a factor of n by doing something clever. I like the entropy proof, which is not a surprise. And then ours also shaves off an exponential factor from the norm bound. I think that this picture is the way to view our results, that ours fits in here. It's the matrix analog of Bregman, I would say. It's similar, and it helps me remember it.
But under some conditions. Under some conditions.
Just as Bregman's doesn't literally give you an exponential savings, it only gives you an exponential savings when these degrees are big. Ours doesn't literally give you an exponential savings, it only gives you an exponential savings when the thing's not like a permutation matrix. To say it back up here, Bregman's result gives you literally no savings if the graph is a perfect matching and delta is 1. And then Bregman actually is not improvement at all. And that's the exact same sense of non-improvement that we have when the thing is a perfect matching, when the thing is a permutation matrix. So it's only under certain conditions, but it's the same certain conditions that you would expect, like going about your everyday life. But either way, it's still there, and this C isn't literally a C. It's some C that depends on A, and sometimes it's 1, but usually it's not. Thanks for that question. Any other ones? Yeah. Okay.
Prove something, Pat. The math talk.
Thanks. So let me show you a proof sketch of what we did, and then I'll show you a nuts and bolts, honest to goodness proof of Hurwitz's result, because it's so short it fits on a page, which is nice. So here's proof of what we did. So again, permanent, difficult thing, norm, that thing. And our goal is to prove something like the permanence less than not just norm to the n, because that's Hurwitz, but to improve upon it with this extra exponential savings. So step 1 is, surprise, to incorporate randomness that wasn't in the problem at all until right now. The problem had no randomness involved, but that's all I know how to do, so here it is. Surprise, permanent is less than or equal to some sort of expected value of a random variable. But that's not unique to us. That's not like a secret sauce that we just did. That's just a thing. People do this. In fact, people use that exact same one. And then also not a surprise, we want to say this, we want to get an upper bound of the permanent, so we got to get an upper bound in this expected value. And the way we'll do that is we'll say sometimes it's less than something and we're happy. The random variable just happens to be small, in which case we'll just say it's less than happy fixed. Plus the probability that we're bigger than something that would make us happy. In which case we're going to give up the probability that it makes us happy, or I guess doesn't make us happy. And then we'll just give up and just put the maximum that the random variable possibly could be here. And this is quite giving up. Yeah. And then all I have to do is somehow say that this piece right here is unlikely. We're either very small, in which case that makes us happy, or the thing is big, but big doesn't happen very often. Big is so rare to make us happy.
The same things.
They are. I thought about that for a while, and they are. Because we wanted the trade-off to be the same. So we set them equal to each other at some point. But my first instinct was, I should get happy prime. And well, that doesn't matter. And I thought, wait, those literally are the same. But I definitely like the objection, because I also have that objection. So that's it. We somehow, and you might say, well, why did this work? Why did this work? It either worked because we had some sort of intuition or insight, or maybe it worked because we were brave enough to think that it might work, or naive enough to think that it might work. Probably more likely is persistent enough to think that we should keep going, especially because of Ross. I was like, I give up. And Ross said, but Pat, push onwards. It hasn't been solved because people haven't pushed hard enough. Anyway, go Ross. Here's some nuts and bolts in particular. The random variable that we want is going to actually be the one norm of matrix times a vector. And I'll show on the next slide why on earth we want that. It's not literally that, but it's that. And what is x? X is going to be just plus or minus 1 uniform vector, which Professor Vu was talking about in his discrete math talk, which might make a person want to use inverse little wind theory stuff, which is what people had tried. And then we tried something else because we're not as fancy, but it worked. For the expected value, we're going to use a generalized, help me out on this one.
I'm just talking. I say kimchi, but who knows?
Okay, we're going to use one of those, which is the thing you would do if you had a Rademacher sum and wanted to do something like this. Yeah, so we use one of these. And to get this upper tail probability, we use a combination of things, Talleyrand, Hofding, and then some hypercontractivity sort of stuff. But mostly just Talleyrand, you could think. Cool. And I'm just going to show you a proof, and I'll probably call it the day after that. So here's a proof of Gervitz's bound. The permanent is less than norm to the n. And this is actually short enough for anyone who wasn't paying attention to try to come in right now, and it'll work. So step 1, cook up some random variable up there, x, which we're going to select plus minus 1 vector, and we're going to choose it uniformly at random. Then, fun fact, trust me, this permanent equals that expected value. Fun fact, trust me. If you expand it out, the only things that will remain are when the xi's exactly cancel out with each of those xj's, and then it'll get a permutation. If I show you now, it'll take us both like half an hour. If you do it at home, it'll take you like 3 seconds. Just trust me, that's a thing. And if you've seen a couple formulas like that, it's also not a surprising thing. Trust me. All right, great. Now let's pretend you trusted me. So then I'm just going to take, Gervitz is just going to take the absolute values of both sides, push that absolute value on inside, and then these xi's are just plus minus 1 vectors. So this thing right here is just 1. So the thing just simplifies to this. This looks like the 1 norm of a vector, sort of a matrix vector product. I might have screwed up those indices. I don't want to think about it, by the way. But anyway, you push through, you get this. And then here we're going to use AMGM to get this product in terms of a sum. And this thing just literally equals this shenanigan here. You can also just trust me if you want. That permanent of A less than or equal to this thing. Fact. Not difficult because first fact, and then this wasn't very long, but again, you might just want to have to check it at home. And then you just say, well, geez, what do we know about this vector, or this random variable inside these parentheses here? This is a random variable depending highly on the x. And in our proof, all we do is take this random variable and chase it like crazy. But we can say something deterministic about the random variable for all vectors x, in fact. That this thing we want, which is the thing on the inside, less than or equal to this, because I think that's Cauchy Schwarz, yeah. And I think I did it right. It's hard for me to type these slides. Equals this, and then from here to here, it's saying, well, geez, the 2 norm of AX, that's less than this norm of A times the 2 norm of X. That's like the definition of the norm of A. It's the thing that makes that equation true. Because AX doesn't get much bigger than X was times the norm of A. It doesn't get any bigger. And then the norm of X is, the 2 norm is exactly root n, because it's a plus minus 1 vector. So it just literally just equals norm of A. So this thing inside these parentheses is literally just always less than norm of A. So the permanent is literally always just less than norm of A to the n. Boom. Which is a neat result. And our proof that Ross and I do looks at this fact, and then looks at this random variable, and chases it like crazy until everything works out. That's kind of how that boils down. Let's see how I'm doing on time. Well, I like that. Cool. So.
Are you going to get the deep spot tips?
Well, I had this slide. I was right, I do not need. And then I had a thing. So that's all I got. Thanks. Yeah.
You say you're done, but I see there are 3 more slides.
I was going to say that.
Oh.
I was about to ask that also.
That'll teach you to look forward to things in life. That was a great question. Sorry. Any other questions?
Questions? That's not a question.
He's sad that it's over. What a champion. Nephew of the century over there.
Must have been very good. At this point, normally we say the non-committee members will leave the room. I think I'm going to wait.
Okay. You're waiving my right to a private flogging or whatever you guys do.
No, you would probably leave the room also. So,
Oh. I thought there was a period where you grill me
we would
personally.
discuss- No, not really. If we have-
Oh, all right.
Professor Wu already asked all this question. So, why don't we just cancel it?
Let's have the whole thing off this here. Thanks anyway.
All right, well, thanks again.